Bismillahirrahmanirrahim. In the name of Allah, the most beneficent and merciful. Dear student, Assalamu alaikum. My name is Dr. Rana Mehmood, and this is our 7th lecture about single crystal X-ray diffraction. This is the 3rd chapter of our course, X-ray diffraction technique, and the course code of this course is CAM 5134. Dear student, this lecture is the continuation of the previous lecture 3.6, in which we were discussing about the neutron diffraction, in which neutron was being used as a source instead of X-rays beam in X-ray crystallography. So here we are going to discuss about spin polarized neutron. If we want to investigate thin films via this method, then we have to use polarized neutron reflectometry. Individual neutron has a spin half and angular momentum of plus minus h by 2. If we apply an external field, there are only two possible orientation of the neutrons, parallel or anti-parallel to the field. So these two possible orientation are shown in the figure on right side, in which its lower spin is downward and upper spin is upward, and the angular momentum of the lower spin is minus half h, and the angular momentum of the other upper circle or the spin of the neutron as plus 1 by 2 h value. Here we see that the polarization can be expressed in scalar form as P is the polarization into n plus minus n minus divided by n plus plus n minus. Here n plus and n minus are the number of spin up and down, that is the number of spin up and spin down neutrons respectively, where P can be expressed as P is equal to F minus 1 divided by F plus 1, where F can be calculated by dividing the upward spin n plus of the neutron divided by the downward spin of the neutron n minus. This F is called the flipping ratio, and this is the measurable quantity in scattering experiment. Spin flip and non-spin flip scattering. At any reasonable temperature, field nuclear movement are oriented randomly at each side in a material. The interaction of the neutrons with this array of random vector lead to incoherent scattering. And if the nuclear moment is perpendicular to the neutron polarized vector, then neutron moment is flipped by scattering event. And if it is parallel to the polarization vector, then no flip will occur. So spin flip scattering has twice the intensity of neutron flipping. Here is the diagrammatic view of the spin flip. So spin flip are downward and upward, are shown here. On left side there is a spin flip and non-spin flip occurs as that is shown on the right side. Here we will discuss what is ferromagnetic. For a ferromagnetic, the applied field determine both the nuclear spin quantization axis and the electron spin direction. So they become parallel to each other and no spin flip occurs. However, if the field is applied in any general direction in the scattering plane, both the spin flip and the non-spin flip scattering take place. And in antiferromagnetic, for antiferromagnet material, the applied field does not decide the electron spin direction. So, the neutron spin quantization axis is not necessarily parallel to the electron spin direction. Thus, the entire scattering is mostly spin flip in case of antiferromagnet materials. Magnetic structure of manganese oxide. This figure 3.19, in which antiferromagnetic superstructure in manganese oxide, iron oxide and nickel oxide, showing pseudo-cubic unit cell for which a supercell is equal to 2a subshell. Oxygen position are not shown in this figure. Manganese oxide, nickel oxide and iron oxide order antiferromagnetically. After taking into account the unpaired spin, the magnetic unit cell as the atomic arrangement may suggest. So here is powder neutron diffraction data for manganese oxide, which is taken in comparison with X-ray analysis at 293 Kelvin, and it is also taken by changing the temperature for neutron diffraction technique. Once it was taken at 293 Kelvin and after that it was taken at 80 Kelvin. So difference in the peaks of the planes are observable in the figure 3.20. This figure shows the schematic neutron X-ray powder diffraction pattern for manganese oxide for wavelength equal to 1.542 angstrom. Peaks are assigned as Miller indices for the cubic unit cell. Neutrons data are adopted from Schull, Strazer, and Wolin, and the reference of this figure is given below. The extra peaks are only present in neutron diffraction below a particular temperature. That temperature is known as Néel temperature, where the unpaired spin are ordered. These extra lines are called superlattice lines, which carries the signature of the spin ordering. Here are some applications of the neutron diffraction. So this neutron diffraction can be used in chemistry. It is also used in Other branches of the chemistry like biochemistry, neutron diffraction has its application in engineering, in life sciences, in geological sciences. It is also used in material science, and it has vast application in this material science as well as in archaeology. Applications of neutron diffraction are also given on this slide. That neutron diffraction used for determination of the structure. It is also used in locating the light atoms. It is also being used for heavy metal atoms, for heavy atoms that absorb X-rays strongly. Similar atomic number and isotopes are also in the application of the neutron diffraction, in which this technique works more superiorly as compared to other X-rays techniques. Magnetic properties can be studied by using the neutron diffraction, and single crystal studies analysis can also be done by this neutron diffraction technique. Existing research about this neutron diffraction technique is the study of microstructure in complex micromolecules, fluid, structure of the thin film system is also being under the research of neutron diffraction technique. Atomic arrangement in nanoparticle can also be studied, and different kind of researches are in the process, and these researches also use neutron diffraction technique. In superconductivity of magnesium borate, neutron diffraction is also being used, and the research area like location of the proton in the biomolecular crystal is another aspect of the existing research involving neutron diffraction technique. And the temperature dependence of the resistance of amorphous carbon can also be one of the research topic in which this neutron diffraction technique is being used. Structured determination of evaporated pure amorphous silicon is also a research topic which is being studied these days by different scientists, and this technique also require neutron diffraction technique. The advantages of the neutron diffraction technique is that neutron and magnetic interaction of the similar strength is shown in this technique, and isotopic sensitivity is also studied. Penetrates sample contaminants. Neutron diffraction technique, in which neutron penetrates sample contaminants, and it is sensitive for bulk and buried structures. This technique show simple interpretation, provides statistical average, not single instances. Wavelength, similar to the interatomic spacing, is also one of its main advantage. Every similar energy similar to the thermal energy in matter can be studied by using this technique. We can also reveal the spin structure of complex system where the spin are aligned in an angle less than 180 degree. This technique is also applicable for restrict ferromagnetic material where the two sub-lattice give small magnetization. And the limitation of this technique are it is difficult to focus, so unfavorable for nanoscale magnetism research. But polarized neutron reflectometry can be used for thin films. Figure of merit is defined by product of respective atomic interaction, the cross section, and the available incident flux and square of the magnetic contrast. Due to small incident flux, the figure of merit is less for small sample areas. And the availability of neutron is very difficult because we need nuclear fission reaction. So these are some limitations in which the last but not the least, if the spin axes are normal to the plane of reflection, then no magnetic scattering take place. Only linear scattering will be there. So these are some limitation of the neutron diffraction technique. And the reason for this are a neutron have magnetic movement, so largely scattered by the magnetic moment of electron. All diffraction methods are sensitive to symmetry of the material, and neutron diffraction pattern of an antiferromagnet is different above and below the Néel temperature. So this is our next diffraction technique, which is of the electron diffraction, in which the source which is being used is the electron beam instead of X-ray beam or neutron beams. There we can see the diagrammatic view in which electron gun produces the electron beam, which after passing through the slit strike the crystal present in the path, and after striking it is scattered at certain angles and can be recorded by the recorder or detector. This technique is also known as gas electron diffraction or electron diffraction technique. This electron diffraction referred to the wave nature of electrons. It may be regarded as the technique used to study matter by firing electron at a sample and observing the resulting interference pattern. This phenomena is commonly known as a wave-particle duality, which states that a particle of matter, in this case the incident electron, can be described as a wave. An electron can be regarded as a wave much like sound are water waves. This technique is similar to the X-ray and neutron diffraction technique. History about the electron diffraction technique is that the de Broglie hypothesis formulated in 1924 predicts that particles should always behave as wave. De Broglie formula was confirmed after 3 years for electrons which have a rest mass. With the observation of the electron diffraction in two independent experiments. George Thomas passed a beam of electron through a thin metal film and observed the predicted interference pattern. Around the same time at Bell Lab, Clinton, Joseph, Davison, and Germer guided their beam through a crystalline grid. The principle of this electron diffraction technique can be given as that the crystalline sample interact with the electron beam mostly by interaction rather than absorption. And the intensity of the diffraction depends on the orientation of the planes of atoms in a crystal relative to the electron beam. In explanation of this technique, the electron have wave characteristic which allow them to be used for diffraction experiments. Their wavelength is related to velocity, which is governed by the voltage through which they are accelerated in an electron gun, and is usually about 0.04 angstrom in conventional electron microscopes. The two techniques of electron diffraction and electron microscopy are closely related. The latter is used more widely, and here we shall see briefly the general characteristic of electron diffraction and how it's compared with X-ray diffraction. Electrons interact strongly with the matter, and intense diffraction patterns are obtained from very small samples. Indeed, for transmission studies, the sample should not be thicker than about 100 nanometer, and we know that 1 nanometer is equal to 10 angstrom. If the sample would be thicker than this limit, then the electron may be unable to pass through the sample. This contrast marked with X-ray diffraction. The efficiency with which X-rays are diffracted by matter is low, and for single crystal studies, relatively large crystals 0.05 millimeter or greater in dimensions are usually required. One advantage of electron diffraction is that secondary diffraction commonly occurs because the scattering of the efficiency of electrons is high and the diffracted beams are strong. So the secondary diffraction occurs when these diffracted beams effectively become the incident beam and are diffracted by another set of lattice planes. There are two undesirable consequences of the secondary diffraction. One is that first, under certain circumstances, extra reflection may appear in the diffraction pattern, and care is therefore needed. Very care is needed in their interpretation. Second consequence is that the intensity of different beams are unreliable and cannot be quantitatively used for structure determination. And dear student, in this lecture, firstly we have studied the remaining portion of our previous lecture in which we were discussing about the neutron diffraction technique. And after finishing that neutron technique, now we have started our next diffraction technique, which is about electron diffraction, in which the source is electron beam instead of neutron and X-ray beams. So in this lecture, we have studied the basic about the electron diffraction. We have also studied the principle, and then after that we started the explanation about this electron diffraction technique. The remaining portion of the explanation will be discussed in the next lecture coming out. That will be 3.8 lecture of this single crystal X-ray diffraction. So I hope I will come back soon with that lecture with the remaining explanation of this electron diffraction technique. So till then, Allah Hafiz. Thank you very much.